Thank you for having me here today. I'm going to talk to you about the relationship between AR and developments in neuroscience. So one of the main goals of neuroscience at the moment, and one of the goals of AR, is to create increasingly high fidelity representations of real-world objects. And so what I want to talk to you about today is how recent research in the neuroscience of realness can help us make informed decisions about how to develop AR products, but also how AR can help us to find out more about human brain function in naturalistic contexts. So the main idea that I want to convey is that in order for us to make the most important developments in both neuroscience and AR, it's critical that we understand some of the fundamental differences between real-world objects and images in their various forms. So the differences between real objects and images have long been known to artists such as René Magritte. And not only that, but there's been a long history of research, both in vision science and many commentaries from philosophers about the fundamental differences between real objects and images. And many vision scientists have raised concerns over the years about the extent to which images are actually similar to their real-world counterparts. So we might just pause for a minute to think about, this may seem like a basic question, but what are the fundamental differences between real objects and their images? So real objects like this, they're tangible substances that exist in three-dimensional space. This mug has a definite surface texture and compliance and weight. When I look at this object with two eyes, I get stereo information that tells me about more information about the three-dimensional shape of the object. We also know that because I have these stereo cues and I'm able to tell the exact size and distance and location of this object with respect to myself. But perhaps most importantly, real objects, unlike images in their various forms, afford genuine grasping and interaction, so I can grasp this mug and use it to drink a cup of coffee. So despite these differences between real objects and images, researchers in human neuroscience have stuck with the overarching assumption that real objects are two-dimensional images are appropriate proxies for investigating the way the brain responds to real objects. But the fundamental problem with this approach is that the human brain, as some of the others have mentioned during the series of talks here, the human brain has evolved fundamentally to allow us to perceive and interact with real objects and environments. Now, support from this idea comes from research in developmental psychology. So this is actually a photograph of one of my daughters when she was 9 months old. And we know from beautiful research by someone called Judy Deloche that she's highlighted the phenomenon of manual investigation of images by 9-month-old infants. So for example, when we present a very young child with a high-resolution coloured photograph of a toy, young children will reach towards and try to grasp, curl their fingers around the objects on the page as if they're trying to pick them up off the page. So this suggests that images have to be learned to be fully understood. So if we think of different types of visual information as falling along a continuum of richness, from two-dimensional line drawings and images up to three-dimensional stereo images of objects and up to real-world objects at the end of the spectrum. And so the question of interest here is to what degree augmented reality images fall and how similar are they with respect to real-world objects? And if they're different to real objects in terms of human brain function, then what are the most important differences? So the answer to this question, in short, is we don't know yet. But a good place to start, and one of the most important places to start, is looking at how the brain responds to real-world graspable objects like this. So I'm going to tell you today about two different lines of evidence that suggest that real-world objects are coded in a fundamentally different way to various forms of images. But to do this, I'm going to give you a very quick 30-second, I promise, 30-second functional neuroanatomy lesson. So we know that information from the eyes is received at the back of the brain in early visual cortex. And from there, information processing is known to be split into two different anatomically and functionally distinct pathways. a ventral processing pathway that is devoted to object perception, and a dorsal object processing or dorsal processing pathway that is devoted to spatial perception and visually guided action. So for example, if I present you with an image of a cup, then this would activate the ventral perceptual stream. But if I ask you then to reach out and grasp a cup like this, then this would engage the dorsal action stream. Now, one way that we can look at the way that real objects are represented in the brain is to take a reverse engineering approach, where we study how the system breaks down in patients with discrete brain damage. So we know from neuropsychological studies, for example, beautiful work by David Milner and Mel Goodale, and later with the work of Glenn Humphreys, that has shown that patients with damage to the object processing areas in the ventral processing stream are unable to perceive images of everyday objects, a condition known as visual form agnosia. But some of the work in these labs has shown that the very same patients who are unable to perceive an image of an object are nevertheless able to perceive a real-world object when you show it to them. So this work suggests that the dorsal action stream is not only involved in action, but may also be involved in perception related to objects. But critically, it may be involved only for objects that are more realistic or for objects that involve actual grasping and interaction. Now, a second line of evidence that we can look at how to show that real objects might be processed differently in the brain is evidence from functional imaging. And in this case, we can do research in the fMRI scanner, functional magnetic resonance imaging research, in which we can look at brain function by studying changes in blood flow to different parts of the brain. And as you can see, this is a picture of me lying in the fMRI scanner. And as you can see, it's a very highly constrained environment. So obviously it's a very tight physical space. The head, when you're lying in the magnet, is positioned with this head coil. Usually there's a front piece on it as well. You have to lie completely still. So any form of motion, it can contaminate the data and make it worthless. So you have to lie absolutely still. There's really not much opportunity for any kind of movement in the scanner. And then lastly, the MRI scanner itself is a very strong magnet. So most MRI scanners in which we do brain imaging at 3 Tesla, that's the equivalent of about 60,000 times the strength of the Earth's magnetic field. So if you take a ferrous object into that environment, it becomes an instant and deadly projectile. So as a consequence, most of the studies in human neuroscience that have used functional neuroimaging have relied on studies of two-dimensional images that are projected onto a set of mirrors that are mounted on the top of the head coil. Now, as a result of this, we know quite a bit about how the human brain responds to images. In other words, we understand image perception. But what about real objects? In one of the first studies of its kind, I've been developing methods and techniques for presenting real objects in the context of fMRI. Now, to the uninitiated, this might not seem like a big deal, but here are the innovations. So firstly, you'll notice that the head coil, the thing that the subject's head is in, is tilted forwards by about 30 degrees. So this is really important because it allows the subject in the magnet to see the objects directly rather than looking up into a mirror. And this is also important from a processing perspective because the visual and motor systems are aligned in the same coordinate reference frames. Now, we control image viewing time either by LEDs or with MRI-compatible LCD glasses. And the stimulus presentation in this case is controlled by me standing mounting the objects on this turntable in the MRI scanner in real time. What I've found from these studies is that the brain represents real objects in a fundamentally different way to the way it represents coloured photographs of the same items. So what we find is that both in the ventral and the dorsal stream, we see differences in brain responses. So in my lab, at the moment, we've been looking at the range of signatures of realness. In other words, how we might process real objects differently to various forms of images in terms of eye movements and perception, up to attention and memory, and even studies of decision making. Now, this research opens up a number of really exciting opportunities, both for neuroscience and AR. So from a neuroscience perspective, one of the things that we really want to do is to make our work relevant in a translational sense. So we might want to help patients, for example, with brain damage to be able to control an artificial or prosthetic limb. And if we want to understand how real people operate in real-world environments, we maybe need to move beyond the study of images and to look at how the brain responds in a more unified way. In other words, how the ventral and dorsal systems operate in tandem rather than just the ventral stream in isolation. So research with AR will be really fundamental for allowing us perhaps to look at how the human brain responds to more richer, realistic stimuli that are perhaps more relevant for grasping and interaction. So I'd like to thank everyone for listening to my talk today and open up for questions.